Hello everyone and welcome back to chemistry class. In today's video, we'll continue our journey into thermal method of analysis. In today's video, we'll cover Introduction to Thermogravimetric Analysis, also known as TGA, instrumentation of TGA, factor affecting TGA curves, and application of TGA. As we have discussed in introduction video, thermogravimetric analysis is measure of weight change in a material as a function of temperature or time under a controlled atmosphere. Its principal uses include measurement of material's thermal stability, filler content in polymer, moisture and solvent content, and a percent composition of component in a compound. The process involved in TGA is when we introduce any material as a reactant, it will convert to product and evolution of gas happen. A typical thermogram is shown in figure. The horizontal portion represents region where there is no change in mass on heating of the sample, and the curved portion indicate weight loss due to the transformation of the sample or occurrence of chemical reaction. The TGA instrument have 5 key components: furnace, sample holder coupled with temperature sensor also known as thermocouple, analytical balance, furnace with temperature programmer, recorder, and atmosphere control. Let us start with instrumentation of TGA. Number 1. Sample holder. The size, geometry, and material of the sample holder or crucible have an important effect of the TGA curve. In TGA, cylindrical or V-shaped glass cups are used. The sample required in TGA is in the range of 2 to 25 mg. Sample holder are commonly made up of alumina, platinum, quartz or nickel, etc. Key features of sample holder is it must be chemically inert, having low background mass and good thermal stability. Also, there should be no reaction involved or weight change of the holder within the experiment temperature range. Second instrument is sensitive analytical balance. In TGA, the sample mass is recorded over a wide range of temperature, that is ambient temperature to 1800 Kelvin approximately. Continuously measures the mass of sample plus holder with high resolution while temperature changes. Key features for analytical sensitive balance: a rapid response to a weight change over the entire temperature range, and the balance and its operative system should be protected from the evolved gases. The third instrument is furnace. The furnace provides the controlled temperature environment to heat the sample at a definite rate or to hold at constant temperature. Heating can be done using a resistance heater of nichrome or canthal wires. Key features of furnace: the furnace of TGA setup should not be only provide the temperature ranging from ambient to 1800 but also provide a linear variation of temperature with time. The heating rate should be from 0.5 to 25 Kelvin per minute. Fourth instrument is unit for measurement and control of temperature. It measures actual temperature at near the sample and control the furnace to follow the desired temperature program. Temperature measuring devices used in TGA are usually thermocouple, placed as near as the sample as possible. Key feature of this instrument is sensor should measure temperature as close to the sample as practical to minimize error. accuracy and resolution for determining how precisely you can define transition temperature, and stability and reproducibility. And the final instrument in TGA is the recorder. It records and displays the mass data. As the experiment proceeds, it generates the thermogram, mass versus temperature or time. Key features of recorder: it should have high resolution, it should have dynamic range, also it should have sampling frequency for how often mass and temperature are recorded. Higher frequency captures sharper events. Let us now focus on working of thermogravimetry. As we know, it contained key instruments like the furnace, balance, temperature programmer, the recorder, and the sample holder. A small sample is placed in a crucible connected to a sensitive balance inside a furnace. As the temperature rises at a controlled rate, the balance continuously records any weight loss or gain. A thermocouple measures temperature and a computer plot a graph of mass versus temperature called thermogram. Flat line shows stability while downward curve shows decomposition or loss of volatile component. That's how TGA help us study thermal stability and composition of material. Let us now focus on factor affecting thermogravimetric results or thermogram. A TGA curve shows the mass of a substance changes with its time. The first factor is heating rate. It is the rate at which temperature is increased during the experiment. At higher heating rates, the sample heats up faster and heat doesn't reach all part of the sample equally. As a result, decomposition starts later and at a higher temperature, shifting of TGA curve to the right. At lower heating rates, heat transfer is more uniform, decomposition starts earlier, and the curve shifts to the left. Example: calcium oxalate decomposes at 600 degrees Celsius at 5 degrees Celsius per minute, but near 640 degrees Celsius at 20 degrees Celsius per minute. The second factor is sample mass, the total weight of the material taken for analysis. A larger sample absorbs more heat and releases gas slowly, so decomposition is delayed and broader on the curve. Also, a very small sample may not give enough weight change for a clear detection. So, the ideal sampling range is around 5 to 10 milligram depending on the balance sensitivity. For example, a 50 milligram sample shows broad peak while a 5 milligram sample gives sharp peaks. The third factor is nature of the sample, like chemical compositions, crystal form, and purity of the material. Pure substances shows a clear single-step decomposition, while impure samples or mixtures may show multiple steps due to different components. Hydrated salts loses water first, followed by main decomposition. Also, crystalline and amorphous forms may have different thermal stabilities. For example, copper sulfate pentahydrate loses water molecule in several stages before main decomposition. The fourth factor is atmosphere or type of gases, meaning the gas present around the sample, like air, nitrogen, argon, etc. In oxidative atmosphere, oxidation or combustion may occur, sometimes causing mass gain. In inert atmosphere, only thermal decomposition happens, leads to no oxidation. In reducing atmosphere, reduction reaction may occur, lowering the decomposition temperature. For example, calcium carbonate decomposes faster in carbon dioxide free gas than in air. The last but not the least factor is sample holder or crucible material, meaning material and shape of the crucible or pan used to hold the sample is more important. Crucible must be thermally stable and chemically inert. Platinum crucible conducts heat quickly, gives sharp TGA transition. Ceramic or alumina crucible heat more slowly but resist corrosion. If crucible react with sample, error occur. For example, using quartz crucible for strong oxidizer to avoid platinum corrosion. So, till now we have discussed introduction, principle, instrumentation, working, and factor affecting TGA curves. Let us now focus on application of TGA. One of the most important application is determining or identification of gases. Further, the composition of the residue can also be determined. This information reveals the decomposition process of the heated material and permit identification of the formula of the residue. Let's look at two examples: thermogram of calcium oxalate and thermogram of salts like copper sulfate. Let us discuss one by one. Calcium oxalate on heating undergo three main stages. In the first stage, it loses water around 100 to 200 degrees Celsius. In the second stage, decomposition of anhydrous calcium oxalate occur around 400 to 500 degrees Celsius and it forms calcium carbonate. In the third stage, the decomposition of calcium carbonate into calcium oxide occur around 600 to 800 degrees Celsius. When we plot a graph of mass versus temperature, we'll clearly see three different decomposition of calcium oxalate. Let us now focus on thermogram of copper sulfate. On heating, hydrated copper sulfate loses water in steps before decomposing to oxide. In the first stage, it loses 4 water molecules around 110 degrees Celsius. In the second stage, it loses remaining 1 water molecule around 250 degrees Celsius, forming copper sulfate anhydrous. In the third stage, anhydrous copper sulfate decomposes to copper oxide around 600 to 700 degrees Celsius. To summarize, thermogravimetric analysis help chemists determining thermal stability, composition, and decomposition behavior of metal. Thank you for watching this video and stay tuned for more videos like this.